Okay, so the idea now is to work on Boolean algebra and logic gates. So let's start. Uh, let's start with it. So Boolean algebra, and we'll define what is Boolean algebra and logic gates. So let's start with the basics. Let's define that 1 is in Boolean algebra equals for us to true, and 0 equals to false. Those are the basic entity that we will use. Now let's work on operators that are very basic in Boolean algebra. We have the OR operator, which you can also show it like a plus, so plus. And there is a truth table. This is also a definition, a truth table that you can define this logic operator using this truth table. For example, for OR, we can define two variables, and between them we are doing the operator. So we have A and B. I can do A or B. Okay, now we can show the truth table for A or B. And this looks like this. We have A, B, and the OR value. Now we have only true or false for this, for every element, because in Boolean algebra every element can have two options, or it's true or it is false. So A can be true or false, 1 or 0, and B can be true or false, 1 or 0. So in the truth table I should show all the options for A and B and the result or for each one of the options. Okay, so this is the table. So A can be 0, B can be 0, the OR will be 0. A can be 0, B can be 1, OR will be defined as 1. A can be 1, B can be 0, OR will be defined as 1. A can be 1, B can be 1, OR will be defined as 1. So you can understand from the truth table how OR operator behave. It gives me true every time, even one of the elements is true. The only option for OR to give me false is when both elements are false. This is how OR operator behave, and this is how the truth table can tell me how an operator behaves. So we have other operators, and a very important one is the AND operator. You can also define it as like a dot between two elements, A and B. You can also define it like A dot B. Okay? And how AND operator behave? For this, you can show the truth table. So the truth table for AND is like the following. For A and B, we'll have the truth table A, B, and the result AND. Now I need to show all the options for A and B, so let's do it. 0, 0, 0, 1, 1, 0, and 1, 1, and the result AND. Now how AND behave? 0, 0 is 0, 0, 1 is 0, 0, 1, 0 is 0, and 1, 1 is 1. You can now understand that AND behaves like if at least one of them is not true, the result will be false, not true. Only when both are true, the result will also be true. All other options are false. This is how AND behaves. And this is how, again, the truth table show us how the operator behave. Now we have other operators. Now there are operators that operate only on one element. For example, the NOT operators, sometimes defined like this. There are sometimes defined like this, sometimes defined like this. There are symbols for NOT, and it works on only one element. So I do NOT of an element. I can define it as like this. I can define it as like this. I can sometimes. Those are the most common ones. Now again, to define the NOT operator, I can use the truth table, even though it works only on one element. So it will be like here A, here is not. Now it's 0 and 1, those are the options for the element A, and not will be 1 for the opposite for the value we have now, and 0 for this. So this is how the not operator behaves. Now there are, when I'm doing a logic, I don't know, sentence like A and B and all this with or C, and this is not on all of this, there are rules what I'm doing first. For example, A and B times B, what should I do first? How things are, what is the order by which I'm doing things? So the order is order for operators. So the laws, the definition is that firstly I'm doing parentheses. Parentheses are firstly. Then secondly I'm doing not. Then I'm doing and. Then I'm doing or. So if I have A and B and not on each one of them, I initially will do not on this, not on this, and then and just then I will do the or, because not comes before the or. So not, we should do it before the or. Now to define algebraic structure in Boolean algebra, Boolean means I have two options, yes or no, 1 or 0. In order to define such a structure, and I will do like structure, I need to fulfill some rules. This structure should have elements. The structure is defined on elements. Let's call those elements group of elements. Let's call them like this. Okay, and we have two operators. The two operators are or, which we will define as plus, and, which we'll define as dot between the elements. And Huntington, let's call them rules. Huntington's rules should be fulfilled in order to call this algebraic structure in Boolean algebra. One, we should have this group, those group of elements with the operators should be closed in those operators. Namely, for each of the operators, or and, the group should be closed. What does it mean to be closed? That when I'm doing operators between elements in the group, I'm staying within the group. I'm not going to somewhere else. For example, if you can think about it for the natural numbers, this is a closed group. If you are talking about 1 and 2, you will get 3, right? 3 is also in the natural numbers, and 1 is also in the same group. So I did an operator and I stayed with the same group. I didn't get 1 plus 2 equals I. I, of course, is in the complex group, while those ones are in the complex, but if I define them in n, this is not very close to if I define this result, it won't be close. So I need that the operators between elements in the group will stay in the group. So the closedness should be closed for, let's say, B closed for or, and B closed for, that means, for example, 1 and 1 or is 1, and great, it's closed because it stayed in my group of elements. Okay, now 0 and 1 or 1 is 1, again, great. 1 and 0 is 0, and great, it stays in my group. Okay, so I need that the group will be closed in relation to my operators, my two operators, or and. So this is to be closed. Now, I need that there will be a unit element, so we call it unit element. So it should be in relation to each of the operators. For example, for OR, I can say that 0 is the unit operator because is the unit element, because if you think about it, if you take any element and you take in the group, in the Boolean group, and you take OR with it, you doesn't change it. It equals 0 and x, and it equals x. It doesn't change. The same goes for AND, but the unit element is 1 because if you take x and you take AND with 1, or 1 and x, it stays the same. It doesn't change the value of x, right? 1 and 1 is 1. If you think about it, 1 with 1 is 1. 1 with 0 is 0. So it doesn't change. This 1 doesn't change the value of any element in the group if you take the group to be 0 and 1. Okay. Now, commutativeness. Now, remember that all of those are, in order to define an algebraic structure, I need all of this. Now, it's in Boolean algebra, usually we're going to talk about 1 and 0, but this is more generally. Now, let's talk about commutativeness, which is, let me just put it this, okay, which is, if I'm doing x and y, it's the same for y and x. This is for OR, and the same goes for AND. If I'm doing x and y, it's the same as y, x. This is commutativeness, that it doesn't matter what is the order between the elements for each of the operators. The next one is the distributive law. If I'm not, okay, yes, it's the distributive law. So let's call it the distributive law. And maybe I should put it in parentheses because this is a more general definition, and we are going to work on Boolean algebra, but it's more general definition for algebraic structure. So, okay. So the distributive law tells me that if I'm doing some element and another element or another element, I can write it as x and y and x and z, like x, y, or x, z. Okay, I did this with this and this with this, and between them the OR. This is the distributive law in relation to AND. In relation to, yes. So I can say from this that, I should write it. Let's call it the AND operator the AND operator, this operator, is distributive in relation to what? To OR operator. AND operator is distributive in relation to the OR operator, and vice versa. If I'm taking x or y and z, I can say that it's x or y times or and x or z. And now I say that OR is distributive in relation to, as we said before, the AND operator. And this is the distributive law. Great. Now let's continue. Now we are going to talk about the fifth property, which is the complement element. Complement element. Great. Now, what the complement element says? It says that for each, if I have the group with elements, so for each element in this group, exists an element in this group, let's call it this group B, and that's it. Exists a complementary element, which will be called complementary of the X element. This is the complementary. This is how we'll call it. Complementary element. And how we'll define this complementary element? We'll define it such that if I'm taking the two elements and doing OR between them, I will get 1. And if I take the two elements and do AND between them, I will get 0. This is the definition for the complement element. If the element satisfy this property for each element in the group, so complement element property is defined, is satisfied. So this is the fifth property. The sixth property, there are at least two elements. There are at least two elements in the group. We can't have algebraic structure here, which is only with one element. So this is the sixth property. So if I need to define it, so I said that there are two elements, x and y, in the groups, such that x is not equal to y. And now, this is for algebraic structure. All we did was for algebraic structure. Until now. What you see above. Now, if you want to work on Boolean algebra, this is for binary operations, which I mainly did this for 0 and 1 for all the binary states. So let's show the Huntington properties for algebraic structure, which you can see right now for Boolean algebra. Now we'll go to the Boolean algebra side. Let's show the Huntington properties for Boolean algebra. Oh, you know, maybe I will just show you the statements, the laws in the Boolean algebra, which will help us work. What we did so far was enough. There is no point to just repeat it, because I mainly did it for Boolean algebra. I will also use not just or and not. I will use also on or and I will also use the not that I showed you. So let's move to the definitions in Boolean algebra. This will be the next things. So let's work on statements. If you want definitions that will help us in working or Boolean algebra. Okay, so we'll have 11 properties that we will work with. Some of them are by definition, some of them not. We'll start with the first one, which is the identity law, and we quite showed it. So for or and for and, for or we have that a and 0 will have a, and a and 1 will have a. So there is identity element for each operation and then or, and we also saw this. The next one is idempotent. Idempotence, which tells us that the same element with itself in and or in or will give me the exact same element. Yes, a or a is a and a is a, and this is called idempotence. Idempotence. The third property will be annihilation, which quite cause my element to vanish, in the relation that if I do a and a or 1, what will I get? And if I do a or just a minute, can I stop it? Oh no, I can't stop it. Okay, so I wish I will. Can David? יש מרפאות שיניים תכופות 24/7. אליהם, אתה לא צריך להחליט בזה. כן, אמור להיות. כן, יותר ממך. עזוב, זה לא אמור להיות אתה. לא, שיפנה. אין ברירה, אתה לא יכול. תפנה אותו למרפאת שיניים, אין ברירה, דחופה. נראה לי בלי, אתה יכול לתת לו? אני לא יודע, לא נראה לי. אז אם אתה רוצה לתת, תיתן, העיקר שתפנה אותו. Okay, so the annihilation, what it tells me is that it will just cause, or this is not true, I mean 0. It will just eliminate my element. Namely, if I take something or with 1, I will just get 1. If I take something and with 0, I will always get 0. So we just eliminate, and it doesn't matter what is the element, I will always get the same. Now the next one. The next one is the inverse law. Inverse law, which tell me that taking A or B is the same as B and A, and for n is the same, A and B is the same as B and A. The next one. The next one is what we... Oh, wait. Oops. No. I did this the wrong one. What I did here is the commutative law. This is not true what I did. This is the commutative law. Yes, the commutative, and I already said this in here. This is the commutative law. Okay. The inverse law state that if I take an element or its inverse, I will always get 1, and if I take element or its inverse, I will always get 1, element and its inverse, I will always get 0, which is the result of this. Okay? Now, the next one, after commutative, we have the distributive, associative. We didn't do yet the associative, so let's do the associative law or property. What it tells me is that if I'm doing A or B or C, you remember that I said that parentheses comes before O, right? Before OR, right? But I can say that this equals if I'm doing A or B in parentheses or C. So it's the same. The same goes for AND. A and B and C is the same as A and B, and this is and C. This is the associative property. Now, the next one is the distributive law, and we already showed this distributive law, and we already showed this, which states, if you remember, that if I take A and I'm distributive of, if you remember, it depends on the operator, so AND operator is distributive in relation to OR in this way, and OR is distributive in relation to AND in that way. So this is exactly what I'm going to say. So we will start with AND is distributive in relation to OR. So if I'm doing this, it's the same as A times B and A times C. And if I'm doing A or B and C, is the same as A and B times A and C. The next property is that it is the involution law, which said that if I'm taking the inverse of an element by twice, I will get the element again. Namely, if I'm taking A, the inverse, and on this I'm doing the inverse, I will just get again the source, the element itself. This is the involution law. The next one is the well-known De Morgan's law. So in relation to OR, I can say that A and B, if you are taking the inverse, you will get A inverse times B inverse. In relation to AND, A and B inverse will get you A inverse or B inverse. So you are changing this and you putting inverse on them. You are changing this and putting inverse on them. This is the idea of the Morgan's law. The next one is the absorption law. Absorption law. Which said that A and A or A and B, and note that it's not like the distributive law where here we had A, B and C, here I have A and B, and this one I can just say that it equals just A. And if I'm taking A and A or B, I'm getting again A. So it can be quite useful for eliminating elements and things. And the next property, which is the disappearing opposite. So and again it will just help me to eliminate elements in equation. Disappearing opposite. So I take A or A, but now instead of just A here, I take A inverse here. And B, what I get is the disappearance of the opposite. This is the opposite that will disappear. I will just get A and B. The inverse just disappeared. Now, the same goes for and. If I take and of the inverse of A or B, what will I get? I will just eliminate the inverse. I will get, and the operator between them will be and. A and B. Okay, so let's do a very little let's do a very little question so we can see that we understood how to work with it. The question will be, try to change the following equation. Try to change the following equation where x times x and y. X times x and y. X or y. Now, the truth is that you can quite very fast be done with this question, because if you remember the absorption law, we can say that this is like A, this is like A, this is like B, and you can say that this is X. This is straight. You can also go the more, let's say, long road and say that according to distributive law, you can do like x time x, right, according to distributive law, and we have like this one, so I can take this one, so I can say x times x plus x times y. And now if I'm looking on this, x times x is A times A is A, so this one is just x, so I can say that this is just x or x times y. And now I can say that it is like, because this comes before this, I can say that it's the same as this, right? Now I can use the this law and say that it is equals just x. I don't really understand why to do all this long way, but okay, there is this option, I don't know. Okay, so what else? I want to show you other operators that are very useful. The XOR operator, which is very useful. The XOR just tell me that elements with the same value, if I'm doing XOR, it is on two operators, or on two elements, A XOR B. Now, the idea will be that if the elements are the same, I will get false, I get 0. If the elements are different, I will get 1, I'll get true. The full name for XOR is exclusive OR. Namely, the elements must be different in order for us to get true, to get 1. And if they are the same, I'll get false, I'll get 0. So in order to define it, let's define the truth table for OR, for XOR, of XOR. And this will be, again, it between two elements, so it's AB, and then the result XOR. Now, remember the idea, if they are the same, I'll get 0, false. If they are different, I'll get true, I'll get 1. So, if A and B are 0, what I will get? I'll get false, because they are the same. If A is 0 but B is 1, they are different, so I'll get 1. If A 1 but B is 0, so great, they are different, I'll get 1, I'll get true. And if they are the same, 1, 1, again, they are the same, so I'll get false, I'll get 0 with XOR between A and B. There is also what is called XNOR, which is the same as XOR, just the inverse. So every place when there is 0 in XOR, I will get in XNOR 1, and every place where there is 1, I will get 0. That's the idea. Now, there are other important operators. The operator NOR, which again works on two elements, A NOR B, and what I will get in this is that they will be equal. It's like, think of it as about not or. So when you get 1, you get 0. Or will get you 1, just or. Will get you 1. If we're looking at or, it's quite good to see that. So let's do that. Oh, no. If I'm doing or, I will get 0 because both are 0. This will give me 1 because one of them is 1. All of them, right? This is for or. This is the normal or. Now, NOR will just do the inverse on or. This is 1 because or is 0. This is 0, 0, and 0. So it's just the opposite of or. This is NOR. Now, I have the operand NAND. And again, like NOR, it's like not of AND. Not, oh, no. Yes, it's like not of AND, yes. And again, it works on two elements, so it's A NAND B. And if we are going to do the truth table to show you how it works, so you'll see that maybe we start with AND, and then we'll do NAND so you can see it. Again, we're taking A, B, we'll take AND, and then NAND. Okay, so A is 0, 0, 0, 1, 1, 0, 1, 1. In AND, we will get like this, right? It's just 1 when both are 1. In all other options, when they're different or the same but 0, I will get false. This is the definition for AND. Now, NAND will take AND and do negative on it. So it will be 1, 1, 1, and 0. So it will be 0 when both are positive, and all the other options will give me 1 in AND, namely true. So maybe I will show you the logic gates. It just in circuits how the operator that we showed looks on logic gates on circuits. So let's do logic gates, how to draw them. Okay, so the logic gates, let's start. So we have the NOT, the logic gate for NOT. Again, it's taking x and give me x tag or x naught, the inverse. And it looks like this. We start with x, then we are doing this here in a circle, and we are getting the inverse. This is the NOT gate. The next gate is the OR gate. And OR, again, A or B. This is what we are going to do. It's like getting z equals A, or let's do it with x, okay, x and y. X or y, and z equals x or y. And I can say that it's x, and here is y, and then this is how the AND gate looks. Okay. Now the AND gate, which is a x and y, which looks like this: x, y, and I get x and y, namely the z equals x and y. So this is the AND gate, this is the OR gate, and this is the NOT gate. Okay. Now the idea is that NOT is defined as this bubble or this round, so this is NOT. So you can also do things like A NOT, B, and do like the OR gate between them, so doing like this. And now let's add a NOT here, and what you will get, you'll get A NOT, because here is the NOT, or B, and this is the OR, and here I have another NOT, here I have NOT, so I will get NOT on all of this, so another NOT on all of the result here. Okay. Now I can also build other gates. For example, if I want NOR, if I want to do NOR, which is, again, if you remember, NOT or what I can do is take the OR gate and put not on it, on the result. So let's put not here. Okay, and this is the NOR gate. So I can have x, y, and I will have a result of z equals x plus or y and not on them. This is the NOR gate. I can also do the NAND gate. If you remember, the NAND is like not on AND. So I can take the AND gate, which is like this, right? This is the AND, and put a not on it after we are doing the AND here, and I get the NAND gate. We also talked about a XOR. Now XOR looks a little bit different. The XOR gate looks like this, which is exclusive, if you remember, exclusive OR, which is XOR. Now how the gate looks, it looks like this. XY comes here, and then I have this one, and then I have the OR gate. This will show me that this function will give me x y naught or x naught y, which I can also put this symbol for exclusive not. This is the symbol for XOR, exclusive OR. It more commonly looks, more precisely looks like this. So this is the symbol for doing XOR between two elements. Now you can play with it. I can even do exclusive NOR, namely exclusive, and do it on NOR, not OR. How I'll do it? I'll do it like XOR, and instead like this, I will end a not. Will end a not. What I'll get is like this. And why did I get? And I can, it looks like this, the symbol for this. And why did I get this? Because if you think about XOR, which is, if you remember the function like this, which is xy tag plus x tag y. Now do not, because the only change is this. Do not on this, and what you get here, this is like oh, maybe I get it wrong. I think I will get it wrong. Yes, because this is the Morgan. Okay. No. My proof is not good. Essentially, it's not on XOR, but I don't know why it's not just the Morgan on it. Oh. Let me try again. Because I think that this XNOR, which is XOR with not on it, is like the Morgan on this. So if you take this, the Morgan on this, if you take this, and you do this, it's like the Morgan, which is not on XY here, doing like this, and x tag y like this, right? And now this is like, again, the Morgan, x naught and y, but it's not really getting me to what I wanted to do, to what I want to get, so let's forget about it. let's forget about it. I'm not sure why it's not working. Maybe I'm making a mistake and I don't see it, maybe. Okay, and from this you can build some logic gates. You can build a whole logic gate. For example, let's do XOR using only a AND, NOT, and OR. So let's build a, let's call it logic circuit using build logic circuit, and let's build XOR by using, and I want only the very basic gates, OR, AND, and NOT. So I get what I get. Remember that A XOR B is what? I can, as we said, it's X not B or A B not, right? A not B or A B not, right? So let's take A, let's take B. Now it's not, so let's do a NOT gate here, like this. And then I will need to take it with B, so let's do AND gate, right? And this B will come, let's do it like, will come here, and now we have here A and B and A NOT, because and I'll get here A NOT B, and this one I will need to do, I got this, now I need to get it with OR with this one, so let's create this one. So I need NOT B, so let's do NOT, so here I get B NOT, and let's do it AND with A, so let's take A from here and put it right over here, this is A, so I get from here A B NOT. Now let's take both this one and that one, and let's combine them with OR, so let's put an OR gate. And I get A not A B or A not B, which is A XOR with B. Okay, so we got A XOR B as we wanted. So you can see how we can build from basic logic gates and other logic gates, which is more complicated. So this was about Boolean algebra and logic gates. I didn't talk about what is called product of sum and sum of products. This I didn't talk about. I'm not sure I want to talk about it. Wait a sec. Okay, let's not talk about it. I don't want to talk about it. I mean, there's not too much I can say about it, so I don't want to talk about it. So about product of sum and sum products I want to talk. Thank you very much. This was about Boolean algebra and algebraic structure and logic gates. So we did Boolean algebra with 0 and 1, We did algebraic structure in this, and we defined the Huntington's criteria and the properties, and we showed the properties for the Boolean algebra and everything. And we also talked about the logic gates like AND, OR, NOT, XOR, and everything. So if we are summarizing from where we started, we started somewhere here, and we started with the operators, with the basic operators, and then we went to the algebraic structure. We defined how to define algebraic structure, what are the properties, Huntington's rules, closed, unit element, commutative, distributive, complement, at least two element. This is to define algebraic structures, and the properties in Boolean algebra. We saw the identity law, the identity idempotence, the annihilation, inverse law, commutative, associative, distributive, involution law, De Morgan's law, absorption law, disappearance opposite, and we saw a very short equation that we solved using those laws. And then we talked about XOR. Why we talked about XOR, I'm not sure. We did another logic gates, XOR, NOR, NAND, and we saw how we represent them in drawings, the different logic gates, and how we can build from basic logic gates a more complex one. For example, we took the XOR and built it from NOT, from AND, and from OR gates. Okay, that's it. Thank you very much. If there are any